Welcome to the second part of maths chapter circles. In this part we are going to study about the results on equal chords, the relationship between length of chords and their distances from the center of the circle. First theorem. So this is theorem number 6 in the first part of the video. First two parts of the video we completed first 5 theorems. So here we are going to continue from theorem number 6. Equal chords of a circle or congruent circles are equidistant from the center or corresponding centers. So here we have two circles with center O and O dash, and we have two chords PQ and RS, and these two chords are equal to each other. You have to prove that these two chords are equidistant from each other. Equidistant means they are equidistant from the center of the respective circles. So equidistant means the perpendicular distance of the center of from this chord is equal to each other. So OL is equal to O dash M. Again I am telling you, in these two circles, congruent circles, first of all the radii are equal because they are congruent circles. So let me just note over here, OP is equal to O dash R and PQ is equal to RS. That is also given. Both the chords are equal. You have to prove that both these chords are equidistant from their respective centers. So OL is equal to O dash M. That's what you need to prove. So for proving that, you need to do a construction. You have to draw perpendicular from O to the respective chords, that is PQ and RS, such that the construction is we have to draw perpendicular from the respective centers onto these chords. So OL perpendicular to PQ and O dash M is perpendicular to RS. These are the constructions. So now we'll do the proof. So in proof we have to consider triangle OPL and triangle O dash RM. In triangle OPL and O dash RM, OP is equal to O dash R because it's given that these two circles are congruent. That means their radii are equal. Angle OLP is equal to O dash MR. Both are 90 degree. And since PQ is equal to RS, half of PQ will be equal to half of RS. So half of PQ is equal to half of RS. Now half of PQ is nothing but PL and half of RS is nothing but RM. Why half of PQ is PL? Because perpendicular drawn from the center of the circle bisects a chord. Theorem number 1, right? So half of PQ is PL and half of RS is RM. So in triangle OPL and O dash RM, OP is equal to O dash R, radii of two congruent circles. Angle OLP is equal to angle O dash MR, both 90 degree, and PL is equal to RM, since half of PQ is equal to half of RS, right? So these two triangles are congruent by RHS test. Right angle, hypotenuse and side of one triangle are equal to right angle, hypotenuse and side of other triangle. That's why these two triangles are congruent by RHS test. Now since these two triangles are congruent by RHS test, we can say by CPCTC that OL is equal to O dash M. So once you prove that OL is equal to O dash M by CPCTC, you can say that equal chords are equidistant from the center of the circle. Equal chords are equidistant from the center of the circle. Now here, this proof which I just explained you, which is written over here, can be proved in a single circle also. So what do you mean by a single circle? Let me show you. So the same proof, I can prove it like this. Oops. Let me draw a circle with a tool. Okay, so suppose we have this circle and we have two chords in this circle. One is over here, which is AB, and the other one is let's say over here, which is PQ, and this is the center of the circle O. This is the perpendicular drawn from the center to the first chord OP. This is the perpendicular drawn from the center of the other chord. Sorry, I'll give it some other name because I've already used the name P. Oops. Correct. So I'm going to give it a name, let's say C and D. Okay, so here also we can prove that equal chords are equidistant from the center. How are equal chords equidistant from the center? See, they have given that PQ is equal to AB. PQ is equal to AB. Here OD was perpendicular to PQ and OC was perpendicular to AB. OD was perpendicular to PQ and OC was perpendicular to AB. We have to prove, hey, this is construction, okay? We have to prove that OD is equal to OC, that is perpendicular distance of these equal chords from the center are equal. So we can prove, and there is one more construction, join OQ and OB. So if you join these two lines, okay, so what do you get over here after joining OQ and OB? So basically OB is equal to OQ. OB is equal to OQ. This angle is 90 degree. This is also 90 degree. And PQ is equal to AB. So half of PQ will be equal to half of AB. So DQ will be equal to BC. So again, these two triangles are congruent by RHS test. And we can say that OD is equal to OC, CP, CTC. That's what we wanted to prove. So equal chords are equidistant from the center. So in a single circle also you can prove this theorem. In two circles also you can prove this theorem. Okay. Now the next theorem is the converse of the previous theorem. Chords of a circle which are equidistant from the center or from the corresponding centers are equal. So here in this figure there are two chords which are equidistant from the corresponding centers. That means OL is equal to O dash M. It is given. So you have to prove, and these are two congruent circles, okay? So their radii will be equal. OP is equal to O dash R. You have to prove that these chords are equal. PQ is equal to RS. That's what you need to prove. Again, you will take these two triangles. You prove them congruent by using RHS test. And then you prove that PL is equal to RM. So can you say that 2 times PL is equal to 2 times RM? Right? But what is 2 times PL? PQ. And what is 2 times RM? RS. What is the reason behind this? The reason is perpendicular drawn from the center of the circle bisects a chord. So if RM is equal to PL, as we have proved by CP/CTC. So 2 times PL will be equal to 2 times RM, and PL and RM both are half of PQ and RS respectively. So 2 PL is PQ and 2 RM is RS. So we proved that if two chords are equidistant from centers of circles, respective circles, then the two chords are equal. Yeah, here the circles must be congruent. That means their radii must be equal. There is one more version of this, that is in the same circle, in a single circle. Suppose we have two chords. Okay, this is AB and this is CD, let's say, and this is the center of the circle O, and these two chords are equidistant. These two chords are equidistant from the center. That means their distance from the center are equal. That means OP is equal to OQ, it is given, and these chords are also equal. That's what you have to prove. So what you will do is you will join OB with OC and you will prove these two triangles congruent, because OB is equal to OC, radii of the same circle. So these two triangles are congruent by RHS test, and then you will prove that PB is equal to QC, and perpendicular drawn from the center of the circle bisects the chord. So 2PB is equal to 2QC, and 2PB is AB, and 2QC is CD. So AB is equal to CD. So the same theorem can be applied on a single circle also. Okay, so that's the converse of the theorem number 6. Okay, there is some activity or something. Okay, so here in this part, it's a small part. All the examples are based on the theorems, the two theorems which we just discussed right now. Okay, so we'll draw a circle. O is the center of the circle, and PO bisects angle APD. PO bisects angle APD. So we have to draw an angle over here, let's say like this. This is angle APD. This is the center, and OP is bisecting this angle. Prove that AB is equal to CD. Where is B and C? Oh. Okay, so my figure is a little different from theirs. Let me redraw this. So what they have drawn is something like this. Oops. Okay, so this is AB and this is CD. They intersect at point P. This is the center of the circle O, and we know that OP bisects angle APD. We have to prove that AB is equal to CD. Okay, so there is no need to write given, because it is already known that what is given from the figure. Prove that also we know. I'll just write construction. Construction is draw OX perpendicular to AB and draw OY perpendicular to CD. OX perpendicular to AB, OY perpendicular to CD. Let me show you. Okay, so proof. In triangle OXP and triangle OYP, in triangle OXP and OYP, angle OXP is equal to angle OYP, both 90 degree by construction. Angle OPX is equal to angle OPY given. It's given that OP bisects angle APD, and OP is equal to OP common. Therefore, triangle OPX is congruent to triangle OPY by AAS test. So both the triangles are now congruent by AAS test, and therefore we can say that OX is equal to OY, CPCTC, and therefore we can say that AB is equal to CD. Why? Since chords equidistant from the center are equal in length. Chords equidistant from the center are equal in length. So OX is equal to OY means these two lines are equal. That means the distance of this chord AB, perpendicular distance of the chord AB from O, and perpendicular distance of chord CD from O are equal, right? So AB is equal to CD, and since AB is equal to CD, we can say that since OX is equal to OY, then we can say that AB is equal to CD. Chords equidistant from the center of the circle are equal in length. So this is how you solve this question using theorem number 6. Next question. In the figure, L and M are midpoints of two equal chords. Okay, so this is how the figure is. Let me just draw it. Okay, L and M are midpoints of two equal chords. So the equal chords are AB and CD, and L is midpoint of AB and M is midpoint of CD. So we'll join LM. Okay, the chords are also equal, that AB is equal to CD, it's given, that's right, given. AB is equal to CD, L and M are midpoints of AB and CD respectively. L and M are midpoints of AB and CD respectively. Okay. लाइव नहीं है. Okay, so L and M are midpoints of AB and CD respectively. That is given to us. And AB and CD are equal chords. That is also given to us. So you have to prove that angle OLM. So where is O? O is the point. O is the center of the circle. I'm sorry, O is not the point of intersection. O is the center of the circle. Let me mark O over here. So angle OLM. Let me join this over here and this over here. Angle OLM is equal to angle OML. That is, these two angles are equal. And angle ALM. Angle ALM is equal to angle CML. Yeah, so that also can be proved. Okay, let's start with the proof. To prove is written over here, so I'm not writing it again. Okay, we know that AB is equal to CD. It is given. And L and M are midpoints of AB and CD respectively. L and M are midpoints of AB and CD respectively. So we can say that AL is half of AL is half of AB, and no need to write this. So we can say that OL bisects AB and OM bisects DC. Right, because L is midpoint of AB, M is midpoint of CD. So OL bisects AB and OM bisects CD. So we know that since line drawn from the center of a circle to the midpoint of a chord is perpendicular to it. Line drawn from the center of the circle to the midpoint of a chord is perpendicular to it. We can say that. Therefore, OL is perpendicular to AB and OM is perpendicular to CD. OL is perpendicular to AB and OM is perpendicular to CD. Why? Because the line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. So this angle is 90 degree. Also this angle is 90 degree. Right? This we have proved. Also, OL is equal to OM. Since equal chords are equidistant from the center. So if these two chords are equal, their perpendicular distance from the center will be equal. The perpendicular distance, as we know now, is OL and OM. So OL will be equal to OM. So in triangle OLM, angle OLM will be equal to angle OML, that is angles opposite to equal sides. Angles opposite to equal sides are equal. So these two angles are equal. So let angle OLM is equal to angle OML is equal to x. Therefore, angle ALM is equal to angle ALO plus angle OLM, right? Angle ALM is ALO plus OLM, which is 90 plus x, right? 90 degree plus x. Similarly, angle CML is equal to angle CMO plus angle OML, that is 90 degree plus x, right? So therefore we can say that angle ALM is equal to angle CML. So both the things we have proved. If you see the question, they have asked to prove number 1 and number 2. We have proved it. So you should understand the steps which I have used to prove these things. First, I proved that it is given that both the chords are equal. So L and M are midpoints of both the chords. So OL and OM will bisect both the chords. They do bisect both the chords. So OL and OM will be perpendicular to the chords because the line drawn from the center of the circle to a chord to the midpoint of a chord is perpendicular to the chord. So OL and OM will be perpendicular to the chord. And since the chords are equal, their distances, perpendicular distances from the center of the circle will also be equal. So OL will be equal to OM. Then in triangle OLM, I proved angle OLM is equal to angle OML, angles opposite to equal sides, and then I proved angle ALM is equal to angle CML by the method which I have shown here. Okay, so that was question number 2. Let's move on to question number 3. What do we have here? Okay, this is the figure. Let me just okay, so this is the figure. In the figure, two equal chords AB and CD of a circle with center O intersect each other at E. Prove that AD is equal to CB. Prove that AD is equal to CB. So we have to do, I'll just first write the given thing. Given is AB is equal to CD. AB and CD intersect at E. Okay. To prove AD is equal to CB and construction join AD and CB. So I'll just join it. Okay. So we only know that these two chords are equal. What else do we know about these two chords? See, to prove AD is equal to CB, AD is equal to CB, we have to prove triangle AED and CEB congruent. But for proving them congruent, what do we know? We just know AB is equal to CD. But that's not even the part of the triangles which we are thinking of about proving congruent. So I think we have to do a construction on both the chords. That is like this. I'll draw a perpendicular. Here also I'll draw a perpendicular. Now, if you see in this figure, both the chords are not at equal distance from the center. It looks like that. But we have to consider that they are at the equal distance, okay? Okay, so this will be P. I'm sorry, this will be P over here, and this will be Q over here. Okay, so let's write the proof. So OP is equal to OQ. What is the reason? Since equal chords are equidistant from the centers. Equal chords are equidistant from the centers. So chords which are equal, their distances from the center of the circle are equal. Right? Since chords AB and CD are equal, their distances from the center OP and OQ will be equal. Okay. What else can we prove from this? Okay, so I think we require to shift our perspective to a better option. Otherwise, this is not working out somehow. Let's see. Okay, so in this question, we don't have to draw this perpendicular. Without drawing the perpendiculars from the centers of the circles to the chords, we can prove it. Okay, so let's see how they have done. So what they are saying is chord AB is equal to chord CD means minor arc AB is equal to minor arc CD because equal chords cut equal arcs. That's one theorem. Equal chords cut equal arcs. Okay, so they are saying that if AD, chord AD is equal, not chord AD, chord AB. They are saying that if chord AB is equal to chord CD, then arc AB, minor arc AB will be equal to minor arc CD. So arc AB is congruent to arc CD. Now if we subtract this common part, that is BD, from both the side, we get arc AB minus arc BD is equal to arc CD minus arc BD. See here the reason they have not mentioned, I will mention it for you. The reason why arc AB is congruent to arc CD is equal chords cut equal arcs. Equal chords cut equal arcs. So AB minus BD is equal to CD minus BD. So AD is equal to CB. Arc AD is equal to arc CB. Arc AD is equal to arc CB. And since arc AD is equal to arc CB, AB minus BD is AD and CD minus BD is CB. Since arc AD is congruent to arc CB, we can say that chord AD is equal to chord CB. Why? Because equal arcs cut equal chords. If arcs are equal, then the respective or the corresponding chords will be equal. If chords are equal, then the respective arcs will be equal. So this is that particular theorem which states the relationship between the chords and the arcs. So it is much more simpler than how we perceived it to be. So it happens. So this is a learning for us. Let's go to the next question. and see what they want. Okay, let's have the figure. Okay, so this is the question and the figure. In figure, equal chords AB and CD of a circle with center O cut at right angles at E. That means they intersect each other at E, which is 90 degree. So in given, I can write AB is equal to CD, cut at right angles at E. AB is perpendicular to CD at E. That is, angle DEB is equal to 90 degree. If L and M are the midpoints of AB and CD, L and M are the midpoints of AB and CD. Prove that OLEM is a square. So L is midpoint of AB, M is midpoint of CD. To prove OLEM is a square. OLEM is a square. Okay, so there is one small construction which they have shown in the figure. Draw or join OE. Okay, let's see how the proof will be. So first of all, these two chords are equal and they are perpendicular to each other. Also, L and M are midpoints of AB and CD. So we can say that OL is perpendicular to AB and OM is perpendicular to CD. Why these two are perpendicular? Since lines drawn from line drawn from center of a circle to the midpoint of a chord are always perpendicular to the chord. The theorem. So since M is midpoint of CD, OM will be perpendicular to CD, and since L is midpoint of AB, OL will be perpendicular to AB. Okay, so therefore we can say that angle OME is equal to angle OLE is equal to 90 degree. Now it is already given that angle DEB or angle MEL is equal to 90 degree. It is already given. Therefore, in quadrilateral OMEL, angle OME plus angle MEL plus angle OLE plus angle MOL is equal to 360 degree. This is angles sum property. So angle OME, which is 90 degree, we have found it out. Angle MEL, which is 90 degree, we have been given. Angle OLE is 90, we have proved, plus angle MOL is equal to 360. Therefore, angle MOL is equal to 360 minus 270, which is 90 degree. So this is also 90, this is also 90, this is also 90 and this is also 90. So we have proved that therefore OMEL is a rectangle since all angles are equal to 90 degree. So we have proved that OMEL is a rectangle. Okay, but we have to prove that it's a square, and we can prove it easily. I'll tell you how. Few more things to understand over here. See, if it is a rectangle, if we can prove that it's a rectangle, we have proved it already. So opposite sides will be equal. So that means OM is equal to LE and OL is equal to ME. Opposite sides of a rectangle. Opposite sides of a rectangle are equal. OM is equal to LE and OL is equal to ME. But it is given that OL is equal to OM. It's not given, we can prove it. OL is equal to OM. Why OL is equal to OM? Since equal chords are equidistant. Equal chords are equidistant from the center. Which chords are equal? AB and CD are equal. Therefore, the perpendicular distance of AB and CD from the center will be same. OM is perpendicular to CD, OL is perpendicular to AB, so OM and OL will be equal. If OM and OL are equal, therefore we can say that LE is equal to ME. So this is maybe 1, 2 and 3. We can say that from 1, 2 and 3 we can say that OM is equal to OL is equal to ME is equal to LE. OM is equal to OL is equal to ME is equal to LE, and therefore OMEL is a square. Okay, so this is how you prove this particular question. Example number 4 is done. Let's go to the next example. If two chords of a circle bisect one another, they must be diameters. Wow, very nice question. Let's draw the figure. So in this circle, you must be wondering why I am making the diameter, the two chords as diameter already, when we have to prove it that they are diameter. So see, if we have to prove that they are diameter, it is better to visualize in the same way before proving it. There is nothing wrong in visualizing that they are diameter. We are not taking them as diameter, but we can at least visualize in the figure. So let's say that AB and CD are two chords and they bisect each other. They bisect each other means they bisect each other at point O. We have to prove that they are diameters. Okay. So there is one small construction which we have to do over here. We have to join AC BC AD and BD with dotted lines. So we'll write given chords AB and CD bisect each other. To prove AB and CD are diameters, construction: join AC, CB, BD and DA and proof. Let's write proof from here. Okay, proof. So in triangle AOC and triangle BOD, can you see these two triangles, AOC and BOD? AO is equal to BO and CO is equal to DO, and angle AOC is equal to angle BOD. Therefore, triangle AOC is congruent to triangle BOD by SAS test. Okay, you must be wondering the reasons, right? So these are given and these two angles are equal because vertically opposite angles. So these two triangles are congruent by SAS test, and therefore we can say that AC is equal to BD CPCTC, and therefore we can say that arc AC is equal to arc BD, because equal chords, since equal chords cut equal arcs, since equal chords cut equal arcs, so arc AC is equal to arc BD. Okay, so these are the two arcs which we have proved equal. But one more, I think, congruency is underway. In triangle BOC and triangle AOD, BOC and AOD, BO is equal to AO, CO is equal to DO. Why? Because they are given, the chords bisect each other, and angle BOC is equal to angle AOD, vertically opposite angles, and therefore triangle BOC is congruent to triangle AOD by SAS test, and therefore we can say that BC is equal to AD. BC is equal to AD, CPCTC, and therefore we can say that arc BC is equal to arc AD. Why? Since equal chords cut equal arcs. Equal chords cut equal arcs. Okay. Now, name this as equation number 1 and name this as equation number 2. So what will happen now? Adding 1 and 2. So we can say that, see, equation 1 was arc AC is equal to arc BD. Equation 2 was arc BC is equal to arc AD. Let's add them. So arc AC plus arc BC is equal to arc BD plus arc AD. So AC plus BC. AC plus BC is AB, arc AB, and BD plus AD. BD plus AD is arc AB. Wait. Oh, yes. I cannot write AB, AB. I'll show you. See, arc AC plus arc BC is arc ACB. Arc ACB is equal to arc BD plus arc AD is arc BAD. So when arc ACB is equal to arc BAD, if you see arc ACB and BAD, BDA, I'm sorry, not BAD, sorry for that, BDA. ACB plus BDA is the whole circle, but arc ACB plus arc BDA is equal to circumference. Is equal to circumference, and therefore arc ACB, sorry, AB, I wrote ABC, arc ACB is equal to half the circumference, right? If you add them, we get the circumference, and they are equal to each other. So one of the arc is half the circumference, and therefore we can say that AB is a diameter. Okay, so similarly we can prove that, since we have proved AB as a diameter, similarly arc CBD can be proved as half circumference, and therefore CD is also a diameter. CD is also a diameter. So this is how you prove that the two arcs, if two chords of a circle bisect one another, then they must be diameters. A little long question, little lengthy one. Okay, let's move to the last question of this part. In figure, OA and OB are respectively perpendiculars to chords CD and EF of a circle whose center is O. Okay, let's write given. OA is perpendicular to CD. OB is perpendicular to EF, and OA is equal to OB. It is given. Prove that arc CE is congruent to arc DF. To prove arc CE is congruent to arc DF. Okay, I don't think that there is any need of any construction. We can do it directly. So let's write the proof here directly. See, we know that OA is equal to OB, and OA and OB are also perpendicular to CD and EF. So we can directly say that CD is equal to EF. chords which are equidistant from the centers are equal in length. Chords which are equidistant from the centers are equal in length. So OA and OB are equal, that is perpendicular distances of the chords from the center are equal. That means the chords must be equal, right? These two chords are at equal distance from the center. That means they will be equal, their length will be equal. Okay, so we proved that CD is equal to EF. So can we say that therefore arc CED is equal to arc EDF? Why? Because equal chords cut equal arcs. Equal chords cut equal arcs. See, we proved that chords CD and EF are equal. So they will cut equal arcs CED and EDF. Arcs CED and EDF are equal. But what is arc CED? It is equal to arc CE plus arc ED, which is equal to arc EDF, which is equal to arc ED plus arc DF. If you cut ED from both the side, you get arc CE is equal to arc DF. That's what we wanted to prove. So this was very straightforward. So these are all the kinds of questions in part B of the chapter. This is the third video, and there are two more parts which are a little bit lengthier. I'm going to continue with them in the next video. So see you in the next video. Bye-bye.